Partitioning the sum of square. Notice that the exam scores in our example differ among students. This difference is known as variation and is measured by a term known as the total sum of square, or SST, which is described by equation 14.9. Recall that SST was first introduced in chapter 11 and appears here in a slightly different form because we are applying it to a dependent variable. But rest assured, it has the same meaning. Formula 14.9, where y is a value of the dependent variable from the sample. Y bar is the average value of the dependent variable from the sample. Unfortunately, equation 14.9 is rather tedious to calculate manually. Equation 14.10 shows a more calculator-friendly version of the SST we can use instead. Let's put equation 14.10 to work with our SNSCSR values from the exam grade example. Simply put, this value measures the square difference between each exam score and the average exam score for the 6 students. The bigger the difference is between the score, the larger the SST will be. If all 6 grades were the same, there will be no variation in Y, which means that the SST would equal 0. Our next step is to partition or divide our SST value into 2 portions. The sum of square regression, or SSR, and the sum of square error, or SSE. Recall that we discussed the sum of square error earlier in the chapter, but have not yet calculated yet. The linear relationship between the 3 sum of square is shown in equation 14.11. To explain the difference between the sum of square regression and the sum of square errors, let's look at the data from our original exam grade example, which is shown again in table 14.4. Notice that student second grade, or 95, is higher than student first grade, or 86. One reason for this difference might be due to the fact that student 2 studied 6 hours for exam, whereas student 1 studied 3 hours. There could also be other reason for the difference in the score not accounted for our example, such as student 1 missing some classes or not getting enough sleep the night before the exam. The sum of square error, or SSE, measures the variation in the dependent variable that is due to variables other than the independent variable. In our grade example, class attendance could be another variable. Equation 14.6 describes the SSE, but I recommend you use the Vrendiel version shown in equation 14.12. This equation requires us to use our SNSCSR values along with the y-intercept, or B0, and the slope, or B1, from the regression equation y cap equal 70.1783 plus 4.1786x that we calculated in the previous section. We now turn our undivided attention to the sum square regression. The sum of square regression, or SSR, measures the amount of variation in the dependent variable, or exam grade, that is explained by the independent variable, or hours of study. Equation 14.13 describes the SSR, but I recommend using equation 14.11 for a simpler calculation. Equation 14.13 describes the SSR, but I recommend using equation 14.11 for a simpler calculation. When we can rearrange equation 14.11 as follows to find the SSR. Remember, the SST equal to 237.5. SST is equal SSR plus SSE, so SSR is equal to SST minus SSE. So SSR is equal to 237.5 minus 74.62 equal to 162.88. In summary, we have partitioned our SST in the following manner. SSR equal to 162.88, SSE 74.62, and SST equal to 237.5. We will put the number to work in the following section. Calculating the sample coefficient of determination. The sample coefficient of determination, or R-square, measures the percentage of the total variation of our dependent variable or grade that is explained by our independent variable or hours of study. We find the coefficient of determination for simple regression using equation 14.14. The value of R-square ranges from 0% to 100%. Higher values of R-square are more desirable than lower ones because we would like to explain as much of the variation of the dependent variable by the independent variable as possible. As we will see in chapter 15, low values of R-square means that we either are using the wrong independent variable or need additional independent variable to explain the variation in the dependent variables. Using the result from partitioning the sum of square for the great example, we have the following. SSR equal to 162.88, SST equal to 237.5, R square is equal to SSR divided by SST equal to 0.686. We can now conclude that 68.6% of the total variation in exam grades can be explained by the hours of study. The value of the coefficient of determination ranges from 0 to 1. The higher the value, the stronger the linear relationship between the dependent and independent variables. The sample coefficient of determination can also be determined by squaring the sample correlation coefficient, R, which we calculated earlier in the chapter as follows. R square equal to 0.828 square equal to 0.686. Conducting a hypothesis test to determine the significance of the population coefficient of determination. The value of R square that we calculated in the previous section represent the coefficient of determination for a random sample of 6 students that was collected from a larger student population. This population has a population coefficient of determination, R square, that is unknown because we have not gathered data on every student who took the exam. We can, however, perform a hypothesis test to determine if the population coefficient of determination, R square, is significantly different from 0 based on the sample coefficient of determination R squared. This test uses the following hypothesis statement. Null hypothesis, p squared less than or equal 0, and alternative hypothesis, p squared greater than 0. A one-tailed or upper test is appropriate here because the coefficient of determination cannot be negative. If we reject the null hypothesis, we have enough evidence from our sample to conclude that a linear relationship exists between the hours studied and the exam score and the student population. For this test, we will use alpha equal to 0.05. The F statistic, which was named after the British statistician Ronald Fisher, is the appropriate test statistic to use for the coefficient of determination. Equation 14.15 shows how to calculate the F-test statistic from this procedure. We need to plug the partition sum of square values from earlier in the chapter. SSR equal to 162.88, SSE equals 74.62. The calculated F-score for this test is as follows. F equal to SSR divided by SSE divided by n minus 2 equal to 8.73. The critical F-score, F-alpha, identifies the rejection region for the hypothesis test. The test statistic shown in equation 14.15 follows the F distribution, which was introduced in chapter 11 with ANOVA. The critical value, or F-alpha, can be found in table 6 in Appendix A. The F distribution has two types of degrees of freedom, D1 and D2, which correspond to the degrees of freedom for the SSR and the SSE. D1 is equal to 1 and D2 is equal to n minus 2 equal to 6 minus 2 equal to 4. The degree of freedom of SSR or D1 always equal to 1 because we have only one independent variable with a simple regression. In chapter 15, or multiple regression, D1 will equal the number of independent variables and can be greater than 1. Using alpha equal to 0.05, the critical F-score found in table 6 in Appendix A is F-alpha equal to 7.709. We can also obtain the critical F-score using Excel f.inv.rt function, which we introduced in chapter 11 as follows: equal to f.inv.rt inside the parentheses 0.05, 1, 4 is equal to 7.709. Because f equal to 873 is higher than F-alpha 7.709 as figure 1411 shows, we reject null hypothesis and conclude that the population coefficient of determination is greater than 0. There appears to be a linear relationship between students' exam grade and their hours of study. We will take a closer look at all of the numbers we saw in the Excel output and figure 14.9c. Figure 14.12 shows these numbers again. The coefficient of determination R squared is shown next to the R squared label equal to 0.686 under the regression statistic heading and is circled in red. The sum of square value that we calculated earlier are shown under the SS column heading in ANOVA table, which is also circled in red. Excel uses the term residual instead of error. The calculated F-score is shown under the F column, and the degrees of freedom, D1 and D2, can be found under the F column. The slight differences between our calculation and the value seen in figure 14.12 are due to rounding. Excel also gives us the p-value for this hypothesis test under the significant F column and the ANOVA table. Recall from chapter 9 that the p-value represents the area under the distribution to the right and or left of the calculated test statistic. The p-value for our exam grade example is shown graphically in figure 14.13. We can also obtain p-value using Excel f.dist.rt function, which we introduced in chapter 11 as follows: equal to f.dist.rt inside parentheses 8.73,1,4 equal to 0.0418. Because our p-value equal to 0.0418, which is less than alpha 0.05, we can reject the null hypothesis, which stated that there was no linear relationship between hours of study and exam grade. By rejecting this hypothesis, we can conclude that there is evidence that a linear relationship exists between these two variables. Thank you.